It's wild that we're basically on a sand spit by the Rio Grande, and that is actually the gateway to Mars. So we want Mars to be a self-sustaining civilization as quickly as possible. I think this can be done in around 20 years.
The reason to go to Mars is that it is the closest thing we have to a twin planet. It's not perfect, bit of a fixer-upper of a planet, but it's just the best we got.
Earth and Mars are relatively close to each other about once every 2 years. And so the goal for SpaceX with Starship is just want to be firing off as many Starships as you can in these windows. And first, obviously, to get cargo, industrial type things, and then humans that can go visit and then hopefully come back.
There is something of an open question as to exactly how much stuff and how many people you need in order to bootstrap a Mars city to be fully industrially independent. It is almost certainly more than 1 million people and more than 1 million tons of stuff. And then the question is, once you're there, what do you do? How do you start to build a city and figure out how to bootstrap from the first 100 tons to the first 1 million tons of stuff there?
In situ resource utilization, something that you might hear a lot about. And that's how do you not bring everything up from Earth, which is highly inefficient and undesirable in a lot of ways. And so both the acquisition of these resources, whether that's ice or whether that's metal or whether that's lunar regolith or things like that. So how do you acquire it? How do you process it? How do you build it?
Ultimately, we'll need lots of power generation, mining in general, propellant production, long duration life support, a lot of construction, and then global communication. This would open up a lot of opportunities for entrepreneurs that want to create things on Mars.
So some things for life in space is a little bit different from life on planets. Some of the solutions do involve physics, but for some reason we've never implemented them. There's low gravity and high radiation, and they both have physics solutions and biological solutions. So for physics would be to centripetally spin the spacecraft, and then you create artificial gravity. And then for radiation, if you have a magnetic field plus dense material equivalent of about 10 meters of water, that's equivalent to our atmosphere, and that would produce radiation. Or we've found ways that we can improve radiation resistance, sometimes 10,000-fold, maybe more, and that would be possible. For microgravity, it's not really practical to have a bunch of centrifuges operating on the planet. It might be practical for, in space or if you're on long missions. So on the planet, it might be better to address the medical consequences, fluids going in the wrong place and osteoporosis and things like that. Right now it's overwhelming the amount of exercise that people have to do and the amount of food they have to eat to compensate for the amount of exercise they do. We know enough about the biology that we could start making inroads into how we could be adapted for microgravity and radiation.
My name is Erica De Benedictis. I'm the founder of a startup called Pioneer Labs, where we're trying to use engineering and evolution to make microbes for use on Mars. Mars is pretty much the combination of basically every way that we usually kill microbes. Individually, we can find organisms on Earth that can tolerate any of those extremes in isolation. And what we don't have is an example of an organism that can tolerate them all together, and I want to make that. We're using a process that's very similar to cultivating roses or breeding dogs called directed evolution. We're trying to take microbe A that is really salt tolerant and microbe B that's really tolerant of low pressure and smush their genomes together so that you get something that's both. And indeed, if you want to deploy biology towards something that it's really good at, which is scale, the scale that it works really well at is a planet. And in fact, on Earth, we've seen this before. So Earth didn't used to be habitable by humans. It didn't used to have oxygen in the atmosphere at all. And it was the arrival of microbes that changed the chemistry of this planet at planet scale because photosynthesis started happening and microbes started converting water into oxygen.
At some point, we're just going to have to terraform the planet. We're probably a few centuries away on that, but it is doable in the same way that building cathedrals was doable in the Middle Ages. That was an effort that took far beyond the lifetime of any one craftsman or architect, and they did it anyway because they knew the end result would be worth it. We're going to have to look at terraforming Mars in the exact same way.
So in terraforming, the question is it possible to do maybe something like what we did on Earth, make it a bit warmer on Mars so that the ice melts and we can have rivers and streams and lakes and oceans and rainstorms, and then presumably plants, and then start to thicken the atmosphere to retain some of that heat and also convert enough of it to oxygen that you can breathe. And a lot of people have thought about this problem for actually more than a century. And the really exciting thing is I think through a combination of engineered nanowires and solar sails mass produced on Earth,
It'd be a little bit like a second moon. Night wouldn't get so cold.
you could actually heat up the surface of the planet to enable liquid water relatively cheaply and quickly. Like we're talking decades and small numbers of billions of dollars, which on the planetary scale, that's doing pretty well.
The light of consciousness is like this tiny candle in a vast darkness, and it could easily go out. So we want to preserve the tiny light of consciousness on Earth, but extend it to Mars and then ultimately to the rest of the solar system. You can just imagine all of these starships waiting in orbit for the planets to align, and then this gigantic star fleet taking over Mars.